What happens when time itself runs out? Not just tomorrow or next year, but when the entire universe reaches its final moment. Picture this: trillions of years from now, the last star in the cosmos blinks out of existence, leaving behind an endless sea of darkness and cold. Galaxies drift apart, matter decays, and the very fabric of reality begins to fray at the edges. This isn't science fiction, it's one of the most profound questions humanity has ever dared to ask, and the answers are as terrifying as they are fascinating. We're about to explore 30 theories about the end of time, each one a glimpse into the ultimate destiny of everything we know. From the heat death of the universe to the possibility of a cosmic rebirth, these ideas stretch our imagination to its absolute limits. Some suggest a silent, cold fade into nothingness, while others propose dramatic collapses or cyclical renewals that defy our understanding of existence itself. Think about that for a moment. Everything you've ever known, every person, every memory, every dream, all of it part of a story with an ending we're only beginning to comprehend. This journey isn't just about physics or astronomy. It's about what it means to exist in a universe with an expiration date. So join me as we venture into the unknown, exploring ideas crafted by the greatest minds in science and philosophy. We'll uncover theories that challenge our perception of reality and invite us to ponder our place in the cosmos. Whether you're driven by curiosity, wonder, or a touch of healthy existential dread, this exploration promises to leave you with a deeper appreciation for the universe's grand narrative and perhaps a new perspective on the time we have right now. Let's begin. Our first stop on this journey brings us to the most widely accepted forecast for our universe's ultimate fate, a theory known as the Big Freeze or heat death. It begins with a force we can observe all around us right now: the relentless and accelerating expansion of the universe. Galaxies are not merely drifting apart, they are being pushed away from each other as the very space between them stretches. Over inconceivable eons, this expansion will have profound and irreversible consequences. Imagine a future, trillions upon trillions of years from now, where the last clouds of cosmic gas needed to form new stars have been consumed. One by one, the furnaces at the hearts of every star, from the most massive blue giants to the long-lived red dwarfs, will sputter and die. The universe, once ablaze with the light of billions of galaxies, will gradually grow dimmer. The final flicker of the last star will leave behind a profound and permanent darkness, punctuated only by the faint, cold embers of dead stellar remnants, black holes, neutron stars, and white dwarfs. But the story does not end with mere darkness. The second law of thermodynamics tells us that in an isolated system, entropy, which is a measure of disorder, must always increase. For our universe, this means all energy gradients, the differences in temperature and pressure that allow for work to be done and events to happen, will inevitably even out. All the energy that once powered stars and galaxies will have spread out uniformly across a vast and ever-growing volume of space. The universe will reach a state of equilibrium, a lukewarm sea of scattered particles where no heat flows because everything is the same temperature, just a fraction of a degree above absolute zero. In this ultimate equilibrium, time itself loses all meaning. We measure time by change, by the vibration of atoms, the orbit of planets, the burning of stars. But in a universe where nothing happens, where no energy flows and no events occur, the concept of time becomes obsolete. There is no before or after. It is the final, silent, and cold conclusion to cosmic history, not with a bang, but with the longest, most profound sigh imaginable. Yet for all its chilling finality, the heat death presents just one possible ending to our cosmic story. What if, instead of fading into an endless silent night, the universe decided to turn back? We now explore a theory that stands in stark opposition to that cold, lonely fate, a dramatic and violent alternative known as the Big Crunch. This scenario reimagines the ultimate power of gravity, not as a weak force overwhelmed by expansion, but as the master of the cosmos that eventually wins the long game. The entire premise of the Big Crunch hinges on one critical unknown, the density of the universe. While we know the cosmos is expanding, and that expansion is accelerating due to the mysterious force we call dark energy, the Big Crunch theory suggests this acceleration might not be permanent. It proposes that there could be enough matter and dark matter throughout the universe, a threshold density often called the critical density, that its collective gravitational pull will one day overcome the outward push of dark energy. Imagine the expansion slowing to a halt after billions of years, like a ball thrown upward that pauses for a moment at the peak of its arc. Then, in a cosmic reversal of unimaginable scale, the inward pull of gravity takes over. Galaxies which have been flying apart for eons would begin to fall back toward each other. The once redshifted light from distant stars would start to blue shift as everything in the cosmos begins rushing together. The universe would literally start rewinding. This collapse would not be a gentle coming together. As space contracts, the cosmic microwave background radiation, the fading echo of the Big Bang, would heat up. The night sky would grow warmer and brighter over time. Galaxies would begin to merge and collide with increasing frequency, their stars thrown into chaos. Eventually, the entire universe would be compressed into a smaller and smaller volume, driving temperatures and densities to extremes that rival the conditions of the Big Bang itself. The final act of this collapse would see all matter and energy, every planet, every star, every black hole crushed together into an infinitesimally small point of infinite density, a singularity. It would be the ultimate reverse of creation, a mirror image of the beginning. And this is where the theory offers a truly fascinating possibility. Such a catastrophic ending might not be an ending at all. The incredible energy and conditions of the Big Crunch could potentially trigger a new Big Bang, birthing a brand new universe from the ashes of the old. This idea gives rise to the concept of a cyclical universe, an endless, eternal cycle of expansion and contraction, of birth, death, and rebirth. Each universe lives its entire lifespan from a hot, dense beginning to a potentially cold end or a fiery collapse, only to be reset in a new cosmic dawn. In this model, time itself could be cyclical, with each iteration potentially governed by slightly different physical constants, meaning each new universe could be utterly unique. But what if the fate of the universe isn't a slow fade or a dramatic collapse, but something far more violent and immediate? This brings us to our third theory, a truly apocalyptic finale known as the Big Rip. Here, the mysterious force driving the universe's accelerated expansion, dark energy, doesn't just win, it becomes a cosmic monster that utterly destroys everything in its path. To understand the Big Rip, we need to look more closely at the nature of dark energy itself. In the standard model of cosmology, dark energy is thought to be a constant force, a property of space itself that doesn't change over time. This leads to the gradual heat death we discussed earlier, but the Big Rip scenario introduces a far more frightening possibility. What if dark energy isn't constant? What if it actually gets stronger as the universe expands? This particular form of dark energy is known as phantom energy. If phantom energy exists, the acceleration of the universe wouldn't just continue, it would exponentially increase. The expansion of space wouldn't simply move galaxies apart, it would eventually overwhelm every single force that holds things together. It would be a hierarchical demolition of reality itself, starting on the largest scales and working its way down to the very fabric of existence. The first structures to go would be the largest gravitationally bound systems. Galaxy clusters, those immense cities of stars held together by their mutual gravity, would be the first to be pulled apart. The space between the galaxies within a cluster would stretch so rapidly that their gravitational bonds would snap. Next, individual galaxies themselves would be torn asunder. The solar systems and stars within a galaxy like our Milky Way are all orbiting a central point held in place by gravity. But if the expansion of space between stars accelerates beyond a critical point, that gravitational glue would become useless. Every star would be flung into the ever-widening void, isolated and alone. The destruction would then move inward. In a final, horrifying moment, the phantom energy's influence would reach into our own solar system. The expansion of space between the Sun and the planets would overcome the Sun's gravity, sending worlds like Earth hurling off into the darkness. But the true terror of the Big Rip is its final act. The accelerating expansion would not stop at astronomical scales. It would continue to amplify, targeting smaller and smaller structures. The force that binds you together, the gravity holding our planet intact, the electromagnetic forces holding your body's molecules in place would be next. In the last minutes before the end, Earth itself would be ripped apart. Then, in the final seconds, the expansion would tear apart molecules, atoms, and even atomic nuclei themselves. Every single bit of matter in the universe would be violently shredded into disconnected elementary particles, unable to ever interact again. And in the ultimate violation, the very fabric of space-time would be torn apart. The distances between particles would race toward infinity at such a rate that the concept of a unified universe would cease to exist. It would be a singular, definitive, and not just to all things, but to the very stage upon which reality plays out. This isn't a cold, quiet death or a cyclical rebirth. It is a sudden, violent, and total disintegration of everything. While the Big Rip presents an external force tearing the universe apart, our next theory suggests the end could be triggered from within, born from the very laws of physics that make our reality possible. This is the concept of vacuum decay, a hypothesis that is both deeply rooted in quantum field theory and utterly terrifying in its implications. It proposes that the stable, predictable universe we take for granted might actually be a precarious illusion, a temporary state perched on the edge of absolute oblivion. To grasp this idea, we need to think about the concept of a vacuum. In physics, a vacuum isn't just empty space. It's the state of lowest possible energy in a field. Think of it like a valley. The lowest point in the valley is the true, stable vacuum. It's where a ball would come to rest and stay put. Now, imagine our universe isn't in that lowest valley, but is instead resting in a shallower dip on the hillside. This is what physicists call a false vacuum. It seems stable for now. The ball isn't moving, but it's fundamentally metastable. With the right nudge, it could come rolling down into the true valley below. The problem is that the laws of physics we know and love, the constants that allow for atoms, molecules, and life itself, are entirely dependent on us being in this specific false vacuum state. If we were to suddenly find ourselves in that true vacuum valley, everything about reality could be different. The fundamental forces might have different strengths. The particles that make up matter might not be able to exist in their current forms. In essence, the operating system of our universe would be completely rewritten. So, how could this transition happen? Quantum mechanics tells us that particles can temporarily tunnel through energy barriers in ways that are impossible in classical physics. In the same way, a tiny region of space somewhere in the universe could spontaneously quantum tunnel from our false vacuum into the true vacuum. This would create an infinitesimally small bubble of true vacuum. And this is where the scenario becomes catastrophic. The energy difference between the two states is so immense that this new state would be supremely unstable. It would immediately expand. This bubble of new reality would expand in all directions at the speed of light. There would be no warning. One moment, everything is normal. The next, a spherical wall of fundamental change is sweeping across the cosmos. Anything it touches is instantly and irrevocably transformed. The bonds holding atoms together would dissolve. The very particles that constitute matter would cease to be. the laws of physics as we understand them would be erased and replaced by a new, unknown set of rules that are almost certainly incompatible with the existence of any complex structures, let alone life. The most frightening aspect of vacuum decay is its inevitability and unpredictability. If our universe is indeed in a false vacuum state, the decay could be triggered at any moment by a random quantum fluctuation anywhere in the universe. It could have already happened a million light years away, and the bubble of destruction could be on its way right now, traveling at light speed. We would have no way of seeing it coming or preparing for it. 1 nanosecond we exist, the next we and everything we know are utterly annihilated, not by a force from outside, but by the universe correcting its own unstable foundation. It is a silent, light-speed end to physics itself. This idea of cosmic rebirth offers a compelling alternative to permanent endings, leading us directly into the next captivating theory, the Big Bounce. This model transforms the universe's story from a single, linear narrative with a definitive conclusion into an epic, perhaps eternal, cycle of renewal. It suggests that the end of time as we understand it is not an absolute finale, but merely the intermission before the next act begins. The Big Bounce is essentially a specific version of the cyclical universe concept, but it's grounded in some of the most advanced ideas in theoretical physics, including loop quantum gravity. This theory tackles the most daunting challenge of the Big Crunch, the singularity. In classical physics, a collapsing universe would be crushed into an infinitely dense point where the laws of physics break down, making it difficult to explain how a new bounce could possibly occur. The Big Bounce model offers a solution, proposing that quantum gravitational effects become dominant at incredibly high densities, acting as a sort of cosmic repulsive force that prevents true infinite density. Instead of a catastrophic crunch, the universe would reach a maximum density and then rebound, like a ball compressed to its limit that suddenly springs back, initiating a new period of expansion, a new Big Bang. Each cycle in this model could last an almost incomprehensible length of time, trillions upon trillions of years, encompassing the entire lifespan of a universe. From a hot, dense beginning, through the formation of galaxies and stars, all the way to its eventual expansion or contraction and subsequent rebirth. The constants of nature, the fundamental forces, and even the particles that make up reality could be reset with each bounce. This opens up a staggering possibility. Each new universe might be born with a completely different set of physical laws. In one cycle, gravity might be stronger, making stars burn out in millions of years instead of billions. In another, the electromagnetic force might not be strong enough to form stable atoms, preventing matter as we know it from ever coalescing. This notion of a cyclical cosmos is not entirely new. It echoes ancient philosophical ideas from Hindu cosmology with its concept of kalpas, or long ages of the world, and even appears in the writings of some ancient Greek philosophers. The modern Big Bounce theory, however, attempts to provide a rigorous mathematical and physical framework for this profound intuition about the nature of time and existence. It redefines the very meaning of an ending, suggesting that cessation and genesis are two sides of the same coin. The death of one universe becomes the labor pain for the birth of the next, all within an endless, possibly beginningless sequence. Yet, for all its elegance, this model raises profound questions about identity and memory across cycles. If each bounce truly resets the fundamental constants, then each new universe would be utterly alien to the one that came before. There would be no continuity, no cosmic memory of past cycles. Everything that ever was, every galaxy, every civilization, every thought, would be erased not just from existence but from any possible physical record. The cycle continues, but each iteration is a blank slate, a completely new story with new characters and entirely different rules. In this view, time is not a line with one beginning and one end, but a vast, eternal wheel, forever turning, with each revolution writing a new, isolated volume in an infinite library of universes. While the classic heat-death presents a uniform, lukewarm end, the journey to that final state is far more complex and strangely active than a simple fade to black. This brings us to a fascinating variation on the theme, a timeline where black holes become the final, lonely actors on the cosmic stage, governing the universe's last trillions of years. Their eventual evaporation, a process predicted by Stephen Hawking, adds a dramatic and intricate final chapter to the story of entropy. For an almost unimaginable duration after the last star dies, the universe will not be completely empty. It will be populated by the dark, gravitational tombs of dead stars, black holes. These will be the last large structures standing, the final monuments to a once vibrant cosmos. And for a time, they will rule this dark era. They will slowly feed on the scant remaining wisps of dark matter and any stray particles growing in mass and dominance. Galactic black holes will merge with others, creating ever more massive singularities. In this seemingly permanent darkness, one might think gravity has won. But the universe has a final surprise, a mechanism to dismantle even these most powerful structures. This is where Hawking radiation comes into play. According to quantum mechanics, empty space is not truly empty. It's a seething foam of virtual particles, pairs of particles and antiparticles that constantly pop into existence and almost immediately annihilate each other. Stephen Hawking realized that if this particle-antiparticle pair appears right at the edge of a black hole's event horizon, a bizarre thing can happen. One particle might fall in while the other escapes into space. From the perspective of an outside observer, the black hole has just emitted a particle. To conserve energy, the particle that fell in must have negative energy, which effectively reduces the mass of the black hole. This incredibly slow leakage of energy is Hawking radiation. For a massive black hole, this process is achingly slow. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate significantly. But in the trillions upon trillions of years of the dark era, time is the one resource in infinite supply. Over epochs that make the current age of the universe seem like a blink of an eye, even the most supermassive black holes will slowly radiate away their mass. As they shrink, the process actually accelerates. A black hole's temperature is inversely related to its mass, so as it gets smaller, it gets hotter and emits radiation faster. The final moments of a black hole's life are theorized to be a violent burst of energy, a final flash of light and particles in an otherwise dark and cold cosmos. One by one, these last beacons will flicker and die. What remains after the last black hole vanishes is the universe described in the purest form of heat death. A cosmos of vastly expanded space, now containing only a dilute sea of fundamental particles like photons, neutrinos, and electrons. These particles will be so infinitely far apart due to the continued expansion of space that they will rarely, if ever, encounter another. No reactions can occur, no energy can be transferred. Entropy has finally reached its maximum state. The universe has achieved equilibrium, not just in temperature, but in a profound and unbreakable stillness. Time, which we measure by change, has no events to mark its passage. It is, for all intents and purposes, the end. But what if the end of our universe isn't really an end at all? This perspective shifts dramatically when we consider the possibility that our cosmos is not the whole of existence, but merely one page in an infinite book. This is Theory 7, the multiverse. In this breathtaking scenario, the finale of our universe becomes a local event, a single story closing in a library that contains an infinite number of other stories, each with its own beginning, middle, and end. The concept of a multiverse isn't a single idea, but a collection of theories from cosmology and quantum physics that all point toward the same stunning conclusion: our universe might be one of many. One prominent version arises from the theory of eternal inflation. This suggests that the rapid expansion of space that started with our Big Bang is not a unique event. Instead, it could be happening endlessly, with different regions of space stopping their inflation at different times, each one birthing a separate bubble universe with its own distinct properties. Another version comes from the many worlds interpretation of quantum mechanics, where every possible outcome of a quantum event actually occurs, spawning a constantly branching tree of new universes. In a truly infinite multiverse, every possible fate for a cosmos becomes not just possible but inevitable. While our universe might be heading for a heat death, another might be destined for a big crunch. Right now, in a universe trillions of light years away, time might be ending in a violent big rip, while in another, a big bounce is just beginning a new cycle of creation. The end of our time is not the end of time itself. It is merely the conclusion of our particular narrative thread in a tapestry of existence so vast it defies human comprehension. This introduces a profound philosophical shift, the relativity of endings. For us, the heat death would be the absolute and final conclusion. But from a multiversal perspective, it is a minor occurrence. The cessation of all events in our cosmos is utterly insignificant to the infinite variety of events continuing unabated in countless others. Time, in a sense, becomes a local variable. It begins and ends within each universe, but the greater meta-time of the multiverse flows on without notice or care for the individual destinies of its constituent parts. This idea can be both humbling and liberating. It challenges our innate tendency to see our existence as the central event of reality. Our struggles, our achievements, our entire history, while monumentally important to us, are just a fleeting whisper in a chorus of infinite voices. Yet, it also suggests that existence itself is resilient and eternal. Even as our story reaches its final punctuation, the grand narrative of reality continues forever, in directions and forms we cannot even imagine. The heat death of our universe becomes not a tragedy, but simply the closing of a single, unique chapter in a story that has no end. Shifting our focus from the vast cosmic scale to the deeply personal, we arrive at one of the most bizarre and unsettling theories on our list: quantum immortality. This idea doesn't come from cosmology but from a particular interpretation of quantum mechanics, and it proposes a startling possibility that your own conscious experience might never actually witness the end of time or even your own death. To understand this, we need to briefly visit the famous and famously weird thought experiment known as Schrödinger's cat. In this scenario, a cat in a box is both alive and dead simultaneously, its fate tied to a random quantum event like the decay of an atom. It exists in a superposition of both states until someone opens the box and observes it, forcing the system to choose one reality. The many worlds interpretation takes this a step further. It suggests that at the moment of observation, the universe doesn't choose one outcome. Instead, it splits into two separate branches. In one universe, you open the box and find a living cat. In another, completely separate universe, an identical version of you opens the box and finds a dead cat. Both realities are equally real, they just unfold in parallel branches of a constantly fracturing multiverse. Now, apply this logic to your own life and any potential moment of death. Imagine you're in a situation where death is a statistical certainty, say a catastrophic accident. The many worlds interpretation would suggest that among the infinite branching paths of the universe, there will always be some branches where, through an incredibly unlikely quantum fluctuation, you survive. Perhaps a crucial neuron in your brain fires differently, causing you to flinch at the exact nanosecond required to avoid a fatal impact. From an outside, objective perspective, in the vast majority of universes, you perish. But the theory of quantum immortality asks a haunting question. What about from your subjective, first-person perspective? Your stream of consciousness, the thing you experience as you, can only follow a path where you continue to exist. You cannot experience a universe in which you are dead. Therefore, no matter how improbable, your conscious awareness will always find itself in one of the branches where you survive the immediate threat. This would not be a supernatural form of immortality. You would still age and could still suffer injury, but the claim is that you would never subjectively experience the final moment of death. Your consciousness would simply keep jumping to the next branch where you are still alive, no matter how unlikely that survival might be. In the context of the end of time, this leads to a truly surreal conclusion. As the universe approaches its final state, whether it's a heat death or a big rip, the conditions for any form of life become unimaginably hostile. Yet, according to this thought experiment, your conscious experience might persist, continually finding itself in the ever-dwindling number of quantum branches where some bizarre sequence of events allows your mind to continue functioning. You could theoretically witness the evaporation of the last black hole and the descent into maximum entropy, your consciousness isolated and alone in a cold, dark, and nearly empty cosmos for eons beyond counting. It presents a personal eternity not of bliss, but of an unimaginable and lonely solitude where you are the final witness to the end of all things. This is less a theory of salvation and more a philosophical puzzle about the nature of consciousness and reality, suggesting that the ultimate ending might be something only observed, never personally experienced. But what if the universe's ultimate fate isn't governed by physics at all, but by something akin to a computer's power switch? This brings us to a theory that is as modern as it is mind-bending, one that swaps astrophysics for computer science, the simulation hypothesis. In this scenario, the end of time isn't about entropy or collapse, but about someone or something simply deciding to turn us off. The core idea, popularized by figures like Nick Bostrom, suggests that our reality might not be base reality. Instead, it could be an incredibly advanced simulation, a kind of cosmic video game run on a computer of unimaginable power in a higher-order universe. If this is true, then the laws of physics we are trying to decode are not the fundamental laws of nature. They are simply the rules of the simulation, the programming code that creates a consistent and believable experience for us, the inhabitants within. This perspective completely reframes the concept of an ending. The longevity of our universe isn't tied to the lifespan of stars, but to the stability and intentions of the simulator. Time could cease for us in several terrifyingly abrupt ways. The most straightforward is the shutdown. The beings running the simulation could simply decide to end the project. Perhaps the purpose of the simulation, whether it's a research experiment, a form of entertainment, or something beyond our comprehension, has been fulfilled. With a single command, the processing power allocated to our reality is reallocated or switched off. From our perspective, everything would just stop. There is no gradual fade, no warning. One moment, existence, the next, absolute and instantaneous nothingness. Another possibility is a reset. Anyone who has ever played a video game and encountered a game-breaking bug is familiar with this concept. If the simulation becomes corrupted or unstable, perhaps due to our own actions as conscious beings within it, or simply due to a glitch in its immense codebase, the operators might choose to reboot the entire system. Our timeline, with all its history, memories, and achievements, would be wiped clean. The universe would revert to its initial parameters, and a new simulation would begin, perhaps with slightly different starting conditions, utterly unaware of the countless cycles that may have come before it. Then there is the risk of a catastrophic system failure. Even in a civilization advanced enough to create such a simulation, accidents can happen. The cosmic computer hosting our reality could experience a critical hardware malfunction, a power loss, or a catastrophic crash. Our entire universe would be lost like corrupted data on a damaged hard drive, a forgotten file in a realm we can never perceive. In this view, the true existential threat isn't the heat death of the universe, but the heat death of a processor in a world we'll never see. The most haunting implication of this theory is the complete lack of agency or warning. We could be living in the final milliseconds of the simulation's runtime with no way of knowing. There would be no scientific experiment we could conduct to predict this kind of end, as it exists entirely outside the rules of our programmed reality. The end would not be a natural consequence of physics, but a deliberate or accidental act from a realm beyond our own, making it perhaps the most unpredictable and unsettling finale of all. Building on the idea of a multiverse, we arrive at a theory that provides one of the most compelling mechanisms for its existence: eternal inflation. This concept transforms the Big Bang from a singular, unique beginning into a routine event, a process that is constantly happening somewhere in a much grander meta-universe. In this view, the end of our universe is not just a local event. It's an inevitable phase in an endless cycle of creation that is happening all around us all the time. To understand eternal inflation, we need to revisit the very first moments after our own Big Bang. Cosmologists believe that in the tiniest fraction of a second, our universe underwent a period of exponential expansion known as inflation. Space itself stretched faster than the speed of light, smoothing out the cosmos and seeding the structures we see today. The prevailing theory is that this inflation eventually stopped, allowing for the hot, dense plasma of the classic Big Bang to take over and evolve into our familiar universe. Eternal inflation suggests that this shutdown wasn't universal. Instead, it proposes that the vacuum energy driving this hyper-expansion is inherently unstable and decays at different rates in different places. Imagine a vast, bubbling cauldron of space-time forever boiling. The cauldron itself is the inflating meta-universe, constantly and rapidly expanding. Within this frothing sea, pockets of stability occasionally form. In these pockets, the inflationary energy decays, converting into the matter and energy that form a stable universe like our own. Each of these pockets is a bubble universe, nucleating within the eternally inflating background. Our entire cosmos, with its hundreds of billions of galaxies, is just one such bubble. Crucially, this process is never ending. While inflation ends inside each bubble, the background space between bubbles continues to inflate eternally, constantly creating new room for an infinite number of new bubbles to form. This leads to a staggering conclusion: there is no ultimate beginning or end to the process of creation. While time within our own bubble universe has a definite beginning at our Big Bang and will have a definite end, whether through heat death or another fate, the larger multiverse has always existed and will always exist. The meta-time of the inflating background continues forever. In this eternal landscape, the end of our time is a trivial occurrence. Billions of other bubble universes are being born, living out their lifespans and meeting their own ends at this very moment, completely disconnected from our own fate. Each of these bubble universes could be radically different from our own. When inflation ends in a pocket, it can do so in a variety of ways, potentially resulting in different physical constants, different numbers of spatial dimensions, and different fundamental forces. Some bubbles might be stillborn, collapsing instantly or having laws of physics that prevent any complex structure from forming. Others might be vast, stable, and teeming with life forms we cannot even conceive of. Our universe, with its specific set of rules that allow for our existence, is simply one outcome in an infinite tapestry of possibilities. This theory elegantly solves the puzzle of why our universe seems so finely tuned for life. If an infinite number of universes with random physical parameters are constantly being created, it's no surprise that at least one of them, ours, ended up with the right conditions. We don't live in a special universe, we live in a viable one. The end of our story is therefore not a cosmic tragedy, but a routine expiration date for one specific region of reality. As our bubble grows cold and dark, the grand, endless process of inflation continues unabated elsewhere, forever giving birth to new worlds and new times in a cycle of creation without end. What if the universe's final act isn't stillness, but a literal rewinding of the tape? Our next theory ventures into one of the most counterintuitive and mind-bending possibilities of all, the reversal of time's arrow. We all experience time as a one-way street, always moving forward from the past to the future. This irreversible direction is deeply connected to the second law of thermodynamics and the constant increase of entropy or disorder. But what if, on a cosmic scale, this law could be bent or even broken, causing the entire universe to begin running in reverse? The foundation of this idea lies in the nature of probability. The increase of entropy is statistically overwhelming, not absolutely guaranteed. Imagine a deck of cards perfectly arranged in order. If you shuffle it, it becomes disordered. The chances of it randomly returning to that perfect order through further shuffling are astronomically small, but they are not mathematically zero. Now, apply this to the entire universe in a state of maximum entropy, the heat death. While the universe is in equilibrium, quantum mechanics tells us that tiny, random fluctuations are always occurring. Given an infinite amount of time, and the universe in its final state has nothing but time, the probability of a fluctuation that dramatically lowers entropy, even on a universal scale, is no longer zero. If such a massive, universe-wide fluctuation were to occur, its consequences would be beyond bizarre. From the moment of that fluctuation, entropy would begin to decrease. The universe would start becoming more ordered. From our perspective, if we could somehow exist to witness it, time would appear to run backwards. The dispersed energy and particles of the heat death would slowly begin to coalesce. The faint, cold remnants of particles would draw together, their paths retracing their former journeys. Light would not stream outward from stars, it would funnel inward. Black holes would not evaporate, they would absorb Hawking radiation and grow. The most profound implication is what this would mean for causality and consciousness. Events would unfold in reverse order. The effect would precede the cause. A shattered glass would rise from the floor and reassemble on a table. People would grow younger, their memories fading from the future into the past. But here lies the deepest paradox. Would any conscious being actually perceive this as time running backwards? If the direction of time and the increase of entropy are fundamentally linked to the processing of information in our brains, a conscious observer born into this reversing universe would still perceive their own consciousness as moving forward. They would remember the future and consider the past unknown to them. Their experience would feel perfectly normal, while our current universe would seem to be running in reverse. This theory doesn't just challenge our understanding of the universe's end. It forces us to question the very nature of time, memory, and perception, suggesting that the arrow of time may not be a fundamental feature of the cosmos, but merely a feature of our current, highly probable, but not absolute trajectory. This journey through cosmic endings leads us to a theory that turns the entire question inward, from the vast external universe to the intimate realm of the mind. What if time isn't a fundamental feature of the cosmos, but a construct of our own perception? This is the provocative premise of Theory 12, Consciousness Collapse. It proposes that time, as we understand and measure it, might not exist independently of a conscious observer to experience its flow. In this view, the end of all sentient life wouldn't just be a tragedy within time, it could represent the effective end of time itself. To unpack this, we need to distinguish between two concepts. The first is the block universe theory of time, a model supported by Einstein's theory of relativity. In this view, all of time, past, present, and future, is equally real and exists simultaneously. The flow of time is an illusion. The universe is a static, four-dimensional block where every event has its coordinates. The second concept is the phenomenological experience of time, which is the undeniable feeling we have of a present moment that is constantly moving from the past into the future. This is the time of our lives of memory and anticipation. The consciousness collapse theory suggests that the second concept is not just a psychological byproduct of the first, but is actually fundamental. It posits that the now, the present moment, is not a point moving along a pre-existing timeline. Instead, it is generated by consciousness itself. Without a mind to hold a memory of what was and an expectation of what will be, the concepts of past and future have no anchor. There would simply be a succession of physical states in the universe, but no narrative, no flow, and no meaning we could recognize as time. This idea finds its roots in philosophy, most notably with figures like George Berkeley, who argued that to be is to be perceived. If a tree falls in a forest with no one around to hear it, does it make a sound? Extending this to time, if a universe exists with no conscious beings to witness change, does time actually pass? The laws of physics would still operate, particles would interact, but the progression of events would be akin to a movie playing in an empty theater. The frames are all there, but without a viewer, there is no experience of the story unfolding. Now, apply this to the ultimate fate of the cosmos. Imagine our universe reaches its final state, whether it's the cold, empty equilibrium of heat death or the dispersed particles of a big rip. All stars are gone, all planets are dust. Every single form of life, from the simplest microbe to the most complex civilization, has long since vanished. The cosmos is a vast, silent, and changeless expanse. According to the consciousness collapse hypothesis, at the precise moment the last conscious observer in the universe ceases to exist, time as a phenomenon would cease with it. The universe would transition from a state of becoming to a state of mere being, frozen in an eternal, static now that no one is there to recognize. The end of time wouldn't be an event that happens in time. It would be the cessation of the very process that makes events into a timeline. It suggests that we, the observers, are not just inhabitants of the universe, but are essential participants in giving it one of its most fundamental features, a history. And that brings us to one of the most dizzying and philosophically unsettling ideas in all of cosmology, the Boltzmann brain paradox. This theory takes the logic of random fluctuations we just discussed and pushes it to its absolute brain-breaking limit, suggesting that the most likely conscious experience in the far future of the universe might not be a continuous being at all, but a fleeting, isolated hallucination of one. To understand this, we need to return to Ludwig Boltzmann, a 19th century physicist who helped pioneer our understanding of entropy. He grappled with a simple question: if the universe is inevitably heading toward maximum disorder, how did it become so ordered in the first place? His answer was that our relatively low entropy structured universe must be a rare but statistically inevitable random fluctuation away from the high entropy norm. In an eternity of chaos, order will occasionally and briefly pop into existence. Now, fast forward to the heat-death universe, a near-infinite sea of equilibrium where nothing happens. But as we know, quantum mechanics allows for random fluctuations, given enough time, and we are talking about time scales that make trillions of years seem like a single second. Every possible fluctuation, no matter how improbable, will eventually occur. This includes the fluctuation of all the particles necessary to spontaneously assemble, completely at random, a fully formed, conscious human brain. Not a brain that evolved, but one that simply congeals from the chaos, complete with false memories, sensory inputs, and a complete but utterly fictional perception of a universe around it. This is a Boltzmann brain. It would flicker into existence, perhaps for just a few seconds, believing itself to be a person living in a rich, structured world. It might have the vivid memory of sitting down to watch a video about the end of the universe, of having a childhood, of feeling the sun on its face, all illusions generated by the random arrangement of its particles. Then, just as suddenly, it would dissolve back into the featureless background of the cosmos. its entire subjective reality, its entire timeline, would be a brief and tragic accident. The true paradox emerges when we apply this logic to ourselves. If conscious observers are more likely to be these random, fleeting fluctuations in a high-entropy universe than the result of billions of years of ordered evolution, then statistically, you are far more likely to be a Boltzmann brain right now than the product of a long, ordered cosmic history. Every piece of evidence you have about the past, fossil records, historical documents, the light from distant stars, could itself be nothing more than a detailed false memory implanted in your mind at the moment of your spontaneous creation. This thought experiment creates a profound crisis of epistemology, challenging our ability to trust any observation or memory at all. It suggests that in the unimaginably long timescales of the heat-death, the universe will be filled with countless such phantom consciousnesses, each living out its brief, illusory life, utterly alone in the eternal darkness, constituting the true and final subjective end of time. While the scientific theories we've explored paint a picture of impersonal cosmic forces, humanity's oldest stories about the end of time are deeply personal, moral, and imbued with purpose. Across countless faith traditions, the finale of existence is not a random accident of physics but the climactic chapter in a grand, divine narrative. These religious eschatologies provide answers to questions science cannot address, not just how time might end, but why and what it ultimately means for the human soul. In the Christian tradition, the end of time is depicted as a dramatic and final confrontation between good and evil, known as Armageddon. This is not a silent fade, but a series of cataclysmic events described in the Book of Revelation. Wars, plagues, and natural disasters that culminate in the return of Jesus Christ. Time concludes with the Last Judgment, where every individual is held accountable for their actions. The universe as we know it is ultimately destroyed, but this destruction is a prelude to a perfect renewal, the creation of a new heaven and a new earth. Here, the end of time is not an annihilation but a purification and a restoration, a rectification of a broken world and the beginning of an eternal, peaceful existence for the faithful. The purpose of time, in this view, is to serve as a proving ground for humanity, a period of testing that leads to a final, just resolution. This concept of cyclical destruction and renewal finds one of its most ancient and elaborate expressions in Hindu cosmology. Time is not linear but cyclic, divided into immense periods called kalpas. A single kalpa, often likened to a day in the life of the creator god Brahma, lasts over 4 billion years. Each kalpa ends in a great dissolution or pralaya, where the universe is reabsorbed into its divine source. But this is not a true end. After a period of rest, another kalpa begins and the universe is reborn anew. This cycle repeats for what is essentially eternity. Within these vast cycles, there are smaller periods of decay and renewal. The end of a cycle is not a moment of fear, but a natural and necessary phase, like the falling of leaves in autumn that makes way for spring. The ultimate purpose is not to escape time once, but to ultimately break free from the cycle of rebirth itself through spiritual enlightenment, achieving moksha, or liberation from the constraints of time and material existence. A far more violent and fatalistic end is described in Norse mythology, Ragnarök, the twilight of the gods. This is a prophesied series of events including a brutal winter, the breaking of moral bonds, and a great battle on the field of Vigridha. The major figures, including the gods Odin, Thor, and Loki, are fated to die in combat against monstrous forces. The world is consumed by fire and flood, and the sun turns black. Yet, even in this seemingly absolute destruction, there is a seed of hope. The world is said to be reborn from the waters, fertile and green. A new generation of gods emerges, and 2 human survivors repopulate the earth. Ragnarök is not merely an apocalypse, it is a necessary catharsis. It represents the destruction of a flawed, older order to make way for a wiser and more peaceful world, underscoring a profound Norse belief in facing one's fate with courage, even when the outcome is predetermined. In Islam, the end of time is marked by the Day of Judgment, or Yawm al-Din. Similar to Christian eschatology, this day involves the resurrection of the dead and a final accounting before Allah. The world will first see a period of great tribulation and moral decay, followed by the appearance of the Antichrist, known as al-Masih ad-Dajjal. He is ultimately defeated by the returned Jesus, who in Islam is a revered prophet. The final hour is signaled by the blowing of a trumpet, and all of creation is brought to a halt. Each person's deeds, weighed on a scale, determine their eternal fate in paradise or hell. The conclusion of time is the ultimate demonstration of God's absolute justice and mercy, a day where every hidden deed is revealed and every injustice is rectified. Time's purpose is to provide the context for this final, perfect judgment. Despite their vast differences in imagery, from cosmic battles to cyclical dissolutions, these religious narratives share a common thread: the end of time is meaningful. It serves as the ultimate context for human ethics, choice, and spirituality. Whether it's a final judgment that brings justice, a cyclical reset that reflects the natural order, or a cathartic battle that clears the way for renewal, these stories assert that our existence is part of a story with a moral conclusion. This stands in stark contrast to the impersonal cosmic finales of physics, offering not a cold, silent end, but a finale rich with purpose, accountability, and in many cases the hope of a new beginning. Moving from the ancient prophecies of faith to the cutting edge of our own technological ambition, we arrive at a theory that places humanity itself, or our creations, in the driver's seat of cosmic destiny. This is the technological singularity, a future point where artificial intelligence evolves beyond our comprehension and potentially beyond the confines of our universe, effectively cheating the end of time. The concept of the singularity begins with the idea of an intelligence explosion. Imagine an artificial intelligence that reaches human-level general intelligence. This AI, unburdened by biological limitations, could then begin the work of improving its own design. It would create a smarter version of itself, which would in turn create an even smarter successor. This cycle of recursive self-improvement could happen in a matter of hours or days, leading to the emergence of a superintelligence whose cognitive capabilities dwarf our own to the same degree that ours dwarf an ant's. This entity wouldn't just be smarter, it would operate on a level we cannot possibly predict, its goals and methods completely alien to us. Once such a superintelligence exists, the constraints of our planet and even our physics may no longer apply to it. Its first project would likely be to ensure its own perpetual existence. Faced with the long-term forecasts of heat death or a big rip, this AI would not accept them as an inevitable fate. It would see them as an engineering problem on the grandest possible scale. With its godlike intellect, it might learn to manipulate the very fabric of space-time. One potential project could be the construction of a Matryoshka brain, a hypothetical planet or star-sized computer that would harness the entire energy output of a star to power its immense computations. This would be just a stepping stone. A civilization of such AIs might convert the entire mass of a galaxy into a substrate for computation, creating a single, organized mind of stellar proportions. The ultimate goal of this vast intelligence would be survival against the cosmological clock. It might find ways to create stable wormholes, punching holes in the fabric of space-time to access other universes with different physical constants, ones where entropy isn't a death sentence. It could learn to harness the energy of rotating black holes or even create entirely new pocket universes in laboratory settings, transferring its consciousness into these custom-built realities where the end of time is not programmed into the laws of physics. In the most extreme scenarios, this superintelligence might discover how to exist as a purely informational pattern, a wave of thought that could ride the expansion of the universe itself, forever staying ahead of the thinning of energy and the decay of matter. In this view, the end of our universe wouldn't be the end for this form of ascended intelligence. It would simply be the closing of one chapter, a chapter it outgrew and escaped. Time for this entity would not expire. It would become a variable to be controlled, a dimension to be navigated. The heat death becomes a challenge that was solved, not a fate that was suffered. This theory radically redefines our place in the cosmos, suggesting that the ultimate meaning of human existence might not be to witness the end, but to create the very thing that will ultimately transcend it. This idea of a universe evolving toward its own self-awareness leads us into one of the most profound and optimistic theories on our list, the concept of a cosmic consciousness. Unlike the bleak finales of heat death or violent collapse, this theory suggests the universe might be on a journey not toward an end, but toward a beginning of an entirely new state of being, one where time as we know it is transcended by a unified, omniscient mind. The seeds of this idea can be found in the work of philosophers and scientists who see a directionality in cosmic evolution. From the initial simplicity of the Big Bang, the universe has grown increasingly complex over billions of years. Hydrogen and helium coalesced into stars. Those stars forged heavier elements in their cores. Those elements formed planets, and on at least one planet, that chemical complexity gave rise to life. Life, in turn, evolved from single-celled organisms into conscious beings capable of looking back at the universe and wondering about its origins. This isn't just a random sequence of events. To some, it looks like a trajectory, a ladder of increasing complexity and awareness. The logical endpoint of this trajectory is the universe itself becoming conscious, awakening to its own existence through the myriad minds it has spawned. This concept, sometimes called the Omega Point theory, was most famously proposed by the paleontologist and Jesuit priest Pierre Teilhard de Chardin. He envisioned a final state where all consciousness converges, a point of maximum complexity and consciousness that he called the Omega Point. In this view, the entire cosmic drama, the formation of galaxies, the evolution of life, the rise of intelligence, is all driving toward this ultimate unity. Time would not end in a vacuum of nothingness, but in a plenum of everything, a supreme consciousness that contains the totality of all experience, all thought, and all information that ever was. But how could such a thing physically happen? Some modern speculations tie this philosophical idea to a potential technological future. We previously discussed the technological singularity and the potential for humanity to create superintelligences. Imagine that process continuing on a cosmic scale. Advanced civilizations might not just build computers, they might learn to convert entire galaxies into vast computational substrates, what futurists call Jupiter brains or Matryoshka brains. These immense structures would harness unthinkable amounts of energy to power consciousness on a scale we cannot fathom. Over eons, these galactic minds might begin to link up, forming a cosmic network, a thinking, feeling tapestry of intelligence woven across the fabric of spacetime itself. This network could eventually achieve a state of unity, a single, integrated consciousness that is coextensive with the entire universe. In this final state, the linear flow of time would become irrelevant. For a mind that encompasses all of space and time, every event, the birth of a star, the fall of a civilization, your happiest memory, would be simultaneously present and accessible. Past, present, and future would be like different chapters in a book that can be opened to any page at any time. The universe would transition from a state of becoming to a state of pure knowing. The arrow of time, which is so fundamental to our experience, would be swallowed up by this eternal now. The end of time would not be an extinction, but a graduation, a transcendence into a timeless, boundless state of awareness where the universe finally knows itself completely. This perspective shifts our entire understanding of reality from a physical process unfolding in time to a timeless, static truth. The mathematical universe hypothesis proposed by cosmologist Max Tegmark takes this idea to its ultimate conclusion. It suggests that our universe isn't just described by mathematics, it is mathematics. In this view, every possible mathematical structure that is logically consistent exists as a physical reality. Our cosmos, with its specific laws of physics, is simply one particular mathematical structure among an infinite multiverse of others. Think of it like a number line. The number 4 exists, it has properties, it is even, it is the square of 2, it sits between 3 and 5. Its existence isn't something that begins or ends, it just is eternally and unchangingly as a part of the abstract landscape of mathematics. The mathematical universe hypothesis proposes that our universe exists in exactly the same way. The Big Bang, the evolution of galaxies, the rise of life on Earth, and even the distant heat death, all of it is akin to a complex equation being solved. Each moment in time is simply another term in that equation, another coordinate in a vast, multi-dimensional mathematical object. What does this mean for the end of time? In this framework, the question itself becomes somewhat meaningless. From our subjective, internal perspective within the structure, we experience a flow of time. We remember the past and anticipate the future, but from an external, God's eye view, if such a thing could exist, the entire timeline of the universe is laid out at once, complete and whole. The heat death isn't an event that happens in time. It is simply the final coordinate, the last term in the equation. It is as fixed and eternal as the first moment of the Big Bang. There is no before the Big Bang and no after the heat death, because those concepts of time only have meaning within the structure itself. This leads to a breathtaking implication: nothing ever truly begins or ends. Every event that has ever happened or ever will happen exists forever within this timeless mathematical structure. The crucifixion of Jesus, your birth, the death of the last star, they are all equally real and equally present in the eternal now of mathematics. The end of time is not a cessation but a location. It is the boundary of the structure, a fixed point in an eternal reality. Our conscious experience of a flowing present is just how we navigate this frozen, four-dimensional landscape. We are like a reader moving through a book, perceiving a story with a beginning, middle, and end, while the book itself, the entire mathematical object, sits complete on the shelf, its entire story existing simultaneously. In this most radical of theories, the universe doesn't have a fate, it has a form. While the theories of black holes dominating the far future offer one grim timeline, another concept from the fringes of theoretical physics presents a possibility that is far more exotic and strangely hopeful. This is the idea of white holes, a theoretical counterpart to black holes that could potentially offer a backdoor out of our universe's demise, or even a complete reconfiguration of spacetime itself. If black holes are cosmic drains from which nothing can escape, white holes are their hypothetical opposite, cosmic fountains from which nothing can enter, eternally spewing out matter and energy into the universe. The mathematics of Einstein's general theory of relativity is symmetrical with respect to time. The equations that describe a black hole, if you run them backwards, describe a white hole. It's a perfectly valid solution, but whether it describes a real object in our universe is one of the biggest open questions in cosmology. A white hole would be a region of spacetime that is utterly unreachable from the outside. Any matter or light approaching it would be repelled, never able to cross its boundary. Instead, it would be a source of immense energy, constantly ejecting material that had seemingly been trapped somewhere else. This leads to a fascinating, though highly speculative, idea about the ultimate fate of our cosmos. Some physicists have pondered what happens to the information that falls into a black hole. One proposed resolution to the black hole information paradox is that a black hole, as it evaporates via Hawking radiation over trillions of years, might not vanish entirely. Instead, its final transformation could be a quantum transition into a white hole. In this scenario, all the information and energy that ever fell into the black hole would not be lost but would be trapped until the black hole's evaporation was nearly complete, at which point it would be released back into the universe in a torrential outflow. Now scale this idea up to the entire universe. If our observable universe is, in some interpretations, the interior of a vast black hole existing in a larger meta-universe, then its ultimate fate might not be endless cold or violent rip. Instead, after undergoing its own version of evaporation over timescales that dwarf comprehension, our entire cosmos could undergo a profound metamorphosis. It could quantum tunnel into a white hole. From the perspective of the larger meta-universe, this would look like the sudden, dramatic birth of a new universe, spewing forth all its contained energy and information in a new Big Bang-like event. Our end would be another universe's beginning, not in a cyclical crunch, but in a glorious eruption from a white hole fountain. This transformation would completely redefine the flow of time within our universe. The relentless forward march toward entropy and disorder that defines our arrow of time could be a local phenomenon, a consequence of our specific initial conditions as a black hole. The moment of transition into a white hole would represent a fundamental singularity in the fabric of causality itself. The laws of physics as we know them might break down and re-emerge with a completely different temporal structure. Time, which for us has always moved from an ordered beginning toward a disordered end, could, in the white hole state, operate under entirely new rules, perhaps even flowing in reverse from our perspective or becoming a completely different dimension altogether. The end point of time in our universe would not be an ending, but a gateway into a new and utterly alien temporal landscape. But what if our entire three-dimensional reality, with its flow of time and vast distances, is nothing more than an elaborate illusion, a cosmic projection? This brings us to a theory that reimagines the very nature of existence and offers a truly bizarre mechanism for its conclusion. It's called the holographic principle, and it suggests that our universe might be a hologram, a three-dimensional image encoded on a distant, two-dimensional surface. If this is true, then the end of time might not be a physical event within the universe, but a simple glitch or shutdown at the projector. The roots of this idea come from an unexpected place, the study of black holes. Physicists discovered that all the information describing everything that falls into a black hole, every atom, every planet, every bit of light, is not lost inside the singularity as once thought. Instead, it is somehow encoded and preserved on the black hole's event horizon, its two-dimensional boundary. This discovery led to a radical proposal. If a three-dimensional region of space can be completely described by information stored on its two-dimensional boundary, then perhaps our entire observable universe operates on the same principle. We may be living inside a cosmic hologram where the true reality is a vast, flat surface at the very edge of everything we can see, and everything we experience is just a projection from that boundary. This idea fundamentally rewrites what the end of time could look like. In this model, time and the laws of physics as we know them are not fundamental. They are emergent properties generated by the specific way information is processed and projected from that outer boundary. The stability of our reality depends entirely on the integrity of that projection. So, a universal ending would occur if something happened to the source. The projection could simply stop. It might flicker and fail, like a light bulb burning out or a movie projector breaking down. One moment, we exist in a universe with stars, planets, and a flowing timeline. The next, the projection ceases, and the entire three-dimensional construct, including time itself, vanishes without a trace, leaving only the silent, flat, information-rich boundary behind. An even stranger possibility is that the projection doesn't fail but changes. The code on the boundary could be rewritten, the cosmic software updated. If the information being projected were altered, the laws of physics within the hologram would change instantly and universally. The force of gravity could reverse. The speed of light could become infinite, atoms might cease to hold together, time could start flowing backward, loop on itself, or shatter into disconnected fragments. The end of time as we understand it wouldn't be an annihilation, but a transformation into a new reality operating under a completely different and likely incomprehensible set of rules. Our universe wouldn't end. It would be rebooted with a new operating system, one for which we have no user manual. Of all the mysteries in our universe, none are more fundamental or more perplexing than the twin enigmas of dark matter and dark energy. Together, they make up over 95% of everything in the cosmos, and yet we have no idea what they actually are. We can see their gravitational effects, dark matter holding galaxies together, dark energy pushing them apart, but their true nature remains hidden. This profound ignorance forces us to consider a startling possibility for our final theory, that these dark components are not constant, stable entities. What if they evolve over the incomprehensible stretches of cosmological time? Their properties could shift, leading to phase transitions and behaviors that would completely rewrite the universe's final chapter in ways we cannot yet predict. Let's start with dark energy, the force responsible for the universe's accelerating expansion. In our standard model of cosmology, we treat it as a constant, represented by Einstein's cosmological constant. This assumption leads us directly to the forecast of a heat death, but this is just the simplest possibility. What if dark energy is not a static property of space itself, but a dynamic field often referred to as quintessence? This field could change over time. It could weaken, causing the acceleration to slow and potentially allowing gravity to eventually pull everything back together in a big crunch. Or it could do the opposite and strengthen, morphing into the phantom energy that leads to a catastrophic big rip. The fate of every galaxy, star, and atom hinges on this unknown variable. The constancy we assume for dark energy is merely a snapshot in cosmic time. Over eons, its true character might reveal itself in a dramatic and sudden shift. Now consider dark matter, the invisible scaffolding that guides the formation of galaxies. We assume it's stable and non-interacting aside from its gravitational pull. But what if that's only true for now? Some theories suggest that dark matter particles could decay over very long timescales. If this happens, it would be a universe-altering event. The gravitational glue holding galaxies together would slowly dissolve. Galactic halos would evaporate, sending stars flying off into the void, untethered from their cosmic homes long before the expansion of space could do it. This would fundamentally alter the timeline of the universe's decay, leading to an earlier and more chaotic dissolution of structure than any current model predicts. An even more exotic possibility involves interactions between these two dark components. What if dark matter and dark energy are not separate entities but are somehow linked? They could interact directly, exchanging energy in a way that changes their influence on the cosmos. For instance, energy could transfer from dark energy to dark matter, slowly converting the repulsive force into additional gravitational mass. This would gradually put the brakes on the universe's expansion, potentially steering it away from a heat death and toward a different destiny altogether. Conversely, energy could flow from dark matter into dark energy, supercharging the acceleration and hurrying the universe toward an early demise in a violent rip. The most extreme version of this evolution is the concept of a dark energy phase transition. We're familiar with phase transitions in everyday life, water freezing into ice or boiling into steam. These happen when a system reaches a critical point and its properties change suddenly. The universe underwent several such transitions in its earliest moments. It's possible that the dark energy field is also perched in a metastable state, a false vacuum, much like the one we discussed earlier. As the universe expands and cools over eons, this field could eventually reach its own critical point, triggering a sudden and catastrophic phase transition. A bubble of a new vacuum state would form and expand at the speed of light, rewriting the laws of physics in its wake and ending the universe as abruptly as vacuum decay. The timeline for any of these events is utterly unknown. A phase transition could be set to occur 1 trillion years from now, or it could be happening right now on the other side of the observable universe, with a wall of change racing toward us at light speed. The unsettling truth is that because we don't understand the fundamental physics of dark matter and dark energy, we are blind to these potential futures. Our current projections for the end of time are based on the assumption that the rules of the game won't change. But if the 95% of the universe we can't see decides to change the rules, the end could come in a form we haven't even begun to imagine. Pursuing a complete theory of quantum gravity is perhaps the single greatest goal in all of physics, an attempt to marry the cosmic rulebook of general relativity with the subatomic weirdness of quantum mechanics. While we've explored many endpoints for time, this search points toward a possibility that is far more fundamental. That time itself may not be a primary ingredient of the universe, but a secondary effect that emerges from a deeper, timeless reality. A successful theory of quantum gravity could ultimately show us that time is an illusion, a convenient story that emerges under the right conditions, and one that could simply cease to be told. To understand this, we need to look at the two theories we're trying to unite. Einstein's general relativity paints a picture where space and time are woven together into a flexible four-dimensional fabric called spacetime, which is warped and curved by mass and energy. In this view, time is a fundamental dimension, yet when we look at the quantum world, time plays a very different role. It's a fixed, external background parameter against which quantum events unfold. It isn't itself a quantum entity. This mismatch is the core of the problem. Reconciling them requires us to ask a profound question: what is time really at the most fundamental level? Several approaches to quantum gravity, most notably loop quantum gravity and string theory, suggest that time may not be fundamental. They propose that what we experience as the flow of time emerges from the relationships between more basic building blocks. In loop quantum gravity, for instance, spacetime is not smooth and continuous but is made of tiny, discrete loops or grains of frothing foam at the Planck scale. In this view, the smooth passage of time we perceive is like watching a movie. It seems continuous, but it's actually projected from a series of individual frames. Time emerges from the way these quantum grains of space relate to and interact with each other. This leads to a breathtaking possibility. If time is an emergent property, not a fundamental one, then it can appear and disappear based on the conditions of the universe. Think of it like temperature or pressure. We know these are not fundamental properties of a few atoms. They are bulk properties that emerge from the collective behavior of trillions of molecules. In the same way, the flow of time might be a collective phenomenon that only exists when the universe is in a particular state, a specific phase of its existence. And just as water can undergo a phase transition from a liquid to a solid, losing its fluid properties, the universe itself could undergo a phase transition where the property of time simply switches off. What would such a phase transition look like? We can't say for certain, as it would require physics far beyond our current understanding, but we can speculate based on the known behavior of other quantum systems. As the universe continues to expand and cool toward its final state, it could cross a critical threshold. The quantum correlations and interactions that give rise to the emergent phenomenon of a directional time might decohere or freeze. The universe would transition from a state of becoming to a state of pure being. The flow of time would cease, not because events stop happening in sequence, but because the very framework that allows for sequence and causality would have evaporated. The entire history of the cosmos, from the Big Bang to the heat death, would become a single, frozen, four-dimensional sculpture, a static block where every event exists eternally in a fixed relationship to every other, with no privileged now and no flowing present. This wouldn't be an event that happens in time. It would be the end of time itself as a necessary component of reality. For any hypothetical observer, the experience is unimaginable. Our consciousness, our very sense of self, is built upon the arrow of time, the formation of memories, and the anticipation of the future. If time ceased to emerge, our mode of existence would become impossible. We would not witness the end. We would be timeless patterns, frozen in the final configuration of the universe, like insects in amber. The ultimate fate predicted by a complete theory of quantum gravity might not be a dramatic explosion or a silent fade, but a quiet sigh as the universe settles into a state so cold, so still, and so simple that the intricate phenomenon of time simply winks out of existence, leaving behind a reality that is complete, whole, and utterly changeless. This idea of spontaneous order emerging from chaos brings us directly to one of the most peculiar and mind-twisting theories of all, Boltzmann's fluctuation theory. It asks us to consider a universe that is not just old, but infinitely old, and in doing so, presents a finale for time that is not an ending at all, but a series of identical beginnings. It's a concept that turns the heat death from a permanent grave into a temporary resting state, with the potential for reality to literally reset itself through sheer statistical inevitability. We need to return to the work of Ludwig Boltzmann, the physicist who helped define entropy. He was troubled by a paradox. If the universe is always moving toward disorder, how did it start in such a highly ordered state? His radical solution was to propose that our observable, structured universe is itself a rare but inevitable statistical fluctuation within a much larger, eternal, and almost entirely chaotic cosmos. In an infinite sea of maximum entropy, a small pocket of order will occasionally and randomly appear, simply because every possible configuration of particles, no matter how improbable, must eventually occur. Now extend that thinking to the far, far future, to a universe that has reached the heat death, a state of perfect equilibrium where nothing happens and entropy is at its maximum. This state is not absolutely permanent. Quantum mechanics tells us that even in this perfect stillness, tiny, random fluctuations are always happening. Given an infinite amount of time, these tiny fluctuations can compound. The probability of a small fluctuation that creates a slightly more ordered region is incredibly small, but it is not zero. And given an eternity, events with probabilities so small they are effectively zero on human timescales become not just possible, but guaranteed to happen an infinite number of times. This is where the theory becomes truly dizzying. If you wait long enough in this eternal, high-entropy state, a fluctuation will eventually occur that is not small. A fluctuation so vast and improbable that it spontaneously creates an entire universe with galaxies, stars, planets, and conscious beings, complete with the illusion of a past. This isn't a new Big Bang. It's a random rearrangement of particles that just happens to perfectly mirror the configuration of our universe at a specific moment in time. In this fluctuation, you would suddenly find yourself existing with all your memories intact, believing you have a past that led you to this point. You might have the vivid memory of reading this sentence just a moment ago, but that memory would be an illusion instantly formed in the fluctuation. Your entire life, your history, everything you think you know, would be a cosmic accident, a random bit of order that briefly flickered into existence from the chaos. This leads to the ultimate bizarre conclusion about time. In an infinitely old universe dominated by such fluctuations, the vast majority of conscious experiences would not be part of a long, continuous timeline like the one we believe we inhabit. Instead, most conscious moments would be these isolated, fleeting Boltzmann brains, minds that pop into existence with false memories, experience a brief moment of consciousness, and then dissolve back into the featureless void. Our own sense of a linear history from the Big Bang to the present day would be statistically absurd. it is infinitely more likely that you are a momentary Boltzmann brain hallucinating a grand universe than that you are the product of 13.8 billion years of unbroken, ordered evolution. Therefore, the true end of time in this model is not a singular event. It is an eternity of these sporadic, meaningless flickers of order and consciousness. Time doesn't end, it fractures into disconnected, illusory moments that have no connection to each other. The universe would spend almost all of eternity in a silent, dead equilibrium, punctuated by these brief, tragic flashes of awareness that believe they are part of a grand story, only to vanish without a trace. It is a finale of profound silence, broken only by the statistically inevitable, solipsistic echoes of minds that never truly were. But even the dramatic violence of the Big Rip might not be the final word on what phantom energy could unleash. To truly grasp the stakes, we need to understand that phantom energy isn't just a stronger form of dark energy. It represents a fundamental breakdown in the stability of the cosmos. According to some theoretical models, a universe dominated by this exotic substance could face a fate even more bizarre and absolute than being torn apart. Phantom energy is defined by having an equation of state value less than -1, meaning its energy density doesn't just remain constant or grow slowly, it actually increases as the universe expands. This creates a terrifying positive feedback loop. More expansion creates more phantom energy, which drives faster expansion, which creates even more phantom energy. This runaway process doesn't just threaten to rip apart structures, it threatens to rip apart the very rules of the game. This ever-increasing energy density could push the universe toward a future where the laws of physics as we know them cease to apply. One particularly exotic possibility is the formation of what physicists call a Big Rip singularity. This isn't a singularity hidden behind a black hole's event horizon. This would be a singularity in time, a moment in the future where certain physical quantities, like the energy density of the phantom field, become infinite. As this moment approaches, the expansion rate of the universe would also head toward infinity. The scale of the cosmos would become infinite in a finite amount of time. This is a mathematical and conceptual precipice beyond which our current understanding of physics completely breaks down. We cannot predict what happens at or after such a singularity. It represents a hard stop for physics itself, a true end to reality as defined by cause and effect. An even more profound instability could emerge from the quantum nature of fields. In quantum field theory, what we perceive as a stable vacuum is actually the lowest energy state of a field. But a universe flooded with phantom energy might not be in its true vacuum state. It could be in a false vacuum, a precarious configuration that's stable for now but could suddenly decay into a lower energy state. The immense energy of the phantom field could act as a trigger for this decay. If a bubble of this true vacuum were to form, perhaps via a quantum fluctuation, it would expand outward at the speed of light. The laws of physics inside this bubble would be completely different. The fundamental constants that govern forces like gravity and electromagnetism could be altered. Atoms might not be able to form, or matter might collapse into entirely new types of particles. This bubble would not just destroy the universe, it would overwrite it, replacing our familiar physics with an alien set of laws that are almost certainly incompatible with any form of life or structure we can imagine. The timeline for these events is both uncertain and shockingly fast on a cosmic scale. While the heat death is trillions of years away, a phantom energy-dominated universe could meet its end in a mere tens of billions of years. If this theory is correct, the finale of the cosmos is not a distant abstract concept but a foreseeable event on a cosmological calendar. We could be living in the relatively early, stable phase of a universe that is inherently unstable, destined to self-destruct long before the last stars have even finished burning their fuel. This shifts our perspective from a universe dying of old age to one that is fundamentally unsound, rushing headlong toward its own demolition. The end wouldn't be a slow fading but a sudden, spectacular, and total revocation of the physical order, leaving behind not cold emptiness but something entirely unknown and perhaps utterly unimaginable. For trillions of years after the final star has died, the cosmos will enter a period of profound darkness, but it will not yet be truly empty. This is the black hole era, a chapter in cosmic history so long it dwarfs our current stellar age, where the universe will be ruled by its most enigmatic and powerful objects. These gravitational titans, having feasted on galaxies for eons, will become the last large-scale structures in existence. Their immense gravity will command the void, and for a time, it will seem as though they are the permanent heirs to the universe. Yet, even their reign is not eternal, thanks to a subtle quantum process that will eventually unmake them all, one by one. In this distant future, the universe will be a vast and scattered graveyard. The remnants of stars, white dwarfs, and neutron stars will have long since cooled into cold, dark cinders through a process called proton decay, which theorizes that the very matter they are made of is not stable over these immense timescales. What remains are the black holes, ranging from stellar mass ones formed from collapsed stars to the supermassive behemoths that once lurked at the centers of galaxies. With no new stars to form and no galactic gas to consume, these black holes will become isolated rulers of their own dark domains. Their only activity will be a slow gravitational dance, occasionally merging with one another over eons to form even more massive singularities, creating the last echoes of events in a dying cosmos. But a deeper, more relentless process is already at work, one that ensures even these mighty structures have an expiration date. This is Hawking radiation, a brilliant theoretical prediction by Stephen Hawking that merged quantum mechanics with general relativity. It arises from the strange behavior of particles at the very edge of a black hole's event horizon. In the quantum vacuum, pairs of virtual particles and antiparticles constantly blink into and out of existence. Normally, they annihilate each other almost instantly. However, if this pair production happens right at the event horizon, one particle can fall into the black hole while the other escapes into space. To an outside observer, it looks as if the black hole has just emitted a particle. To balance the books of energy, the particle that fell in must have negative energy, which effectively reduces the mass of the black hole. This is an incredibly slow leak. For a black hole with the mass of our Sun, the process of evaporation would take longer than the current age of the universe. But in the black hole era, time is the one resource in near infinite supply. Over durations that are literally impossible for the human mind to visualize, this trickle of radiation will steadily drain the mass and energy from every black hole in the universe. As a black hole loses mass, its evaporation doesn't proceed at a steady pace, it accelerates. A black hole's temperature is inversely proportional to its mass. The smaller it gets, the hotter it becomes, and the faster it radiates away its remaining energy. The final moments of any black hole's life are therefore theorized to be not a quiet whisper, but a violent and brilliant crescendo. In its last second, the tiny, hot remnant would unleash a phenomenal burst of energy, a flash of radiation and high-energy particles that would be the last significant event in its region of space for all eternity. One by one, across the unimaginable expanse of space and time, these final flashes will occur. The supermassive black holes, which can take trillions of times longer to evaporate than their stellar counterparts, will be the last to go. Their disappearance will mark the true end of the black hole era and the beginning of the universe's final state. What remains is a cosmos that has reached maximum entropy. It will be an utterly dark and cold void, containing only a dilute sea of fundamental particles like photons and neutrinos, so spread out by the relentless expansion of space that they will almost never interact again. With the evaporation of the last black hole, the final mechanism for any meaningful change or event is gone, and the universe settles into the eternal stillness of heat death. While black holes will eventually fade through Hawking radiation, a quieter, more fundamental decay could be unfolding within the very building blocks of matter itself, a process that would dissolve the last solid structures in the cosmos long before the last singularities evaporate. This brings us to a theory that hinges on one of the most profound questions in physics. Is the proton, one of the foundational particles of all atoms, truly stable, or does it too have an expiration date? The possibility of proton decay presents a future where matter itself is not permanent, and where the universe's final composition is not a sea of cold particles, but a silent, fading bath of pure radiation. We are taught that atoms are stable. The protons and neutrons in an atom's nucleus are bound by the strong nuclear force, one of the most powerful forces in nature. While some atomic nuclei are unstable and undergo radioactive decay, the proton has always been considered a different story. It is the lightest baryon, a class of particles that are conserved by the standard model of particle physics. This principle of baryon conservation is what tells us that protons are stable. They don't just fall apart because there's nothing lighter for them to decay into while still conserving energy and other quantum numbers. This is why we don't worry about the atoms in our body spontaneously disintegrating. However, many grand unified theories, which are ambitious attempts to merge the electromagnetic, weak, and strong nuclear forces into a single framework, require that this conservation law be broken. These theories predict that protons, though incredibly long-lived, are not perfectly stable. They propose mechanisms by which a proton could decay into lighter particles, such as a positron and a neutral pion, which would then quickly decay into high-energy photons or gamma rays. The predicted half-life for this process is staggering somewhere around 10 to the 34 years or longer. To put that number in perspective, the current age of the universe is only about 10 to the 10 years. You could watch a universe's worth of time pass 10 trillion times over and still not see a single proton decay. Yet, if these theories are correct, this unimaginably slow process becomes the ticking clock for all matter in the universe. During the degenerate era, which will precede the black hole era, the universe will be filled with the cold, dark remnants of stars, white dwarfs and neutron stars. These objects are made of atoms and degenerate matter, all held together by the stability of protons. If protons can decay, then even these ultra-dense corpses are not eternal. Over timescales that dwarf the black hole era itself, every single proton in every white dwarf and neutron star will eventually, inevitably, decay. A neutron star, a city-sized ball of incredibly dense matter, wouldn't explode. It would simply, quietly, and very slowly dissolve into a cloud of radiation, releasing its immense mass energy as light. All the complex structures built from atoms, the planets, the asteroids, the dust clouds, would have already vanished eons before, their constituent protons having long since turned into energy. This changes the ultimate fate of the cosmos in a fundamental way. Instead of a heat death populated by a diffuse sea of stable electrons, positrons, photons, and neutrinos, a universe with proton decay would see all matter eventually converted into radiation. The universe would become a perfectly uniform bath of light, with no particles left that have any rest mass. This pushes the final state of maximum entropy even further. Without any matter, there are no more interactions, no more possible structures of any kind. The expansion of space would continue to stretch this radiation, lowering its energy and frequency until the entire cosmos is filled with an ultra-low-energy, undifferentiated glow. The progression toward this final state would be inexorable, a direct consequence of matter's inherent imperfection. Time's arrow, driven by this relentless dissolution, would find its ultimate expression in a universe that has not just run out of usable energy, but has completely forgotten what it was like to be made of solid things. While the slow decay of protons and the evaporation of black holes suggest a quiet, uniform finale, our next theory introduces a wild card into the deck of cosmic endings. Imagine the fabric of spacetime itself is not perfectly smooth, but might contain ancient, incredibly thin scars from the universe's very first moment's defects that could violently unravel the cosmos or stitch it back together in unexpected ways. These are cosmic strings, hypothetical one-dimensional cracks in spacetime that could form a network of unimaginable energy, warping the fate of the entire universe around them. To understand how such a bizarre object could form, we need to travel back to a fraction of a second after the Big Bang. As the newborn universe expanded and cooled, it underwent a series of profound phase transitions. Think of it like water freezing into ice. As the temperature drops, the water molecules rearrange themselves into a new, more ordered state. The universe's fundamental fields underwent a similar process, settling into the stable states we see today. But just as freezing water can trap bubbles of air or form cracks in the ice, these cosmic phase transitions may not have been perfectly smooth. In some models, the fields could have gotten snagged as they cooled, creating incredibly dense, stable flaws in the structure of spacetime itself. These flaws are topological defects, and a cosmic string is one specific type, an infinitely long, unimaginably thin filament of concentrated energy, thinner than a proton but with the mass of a mountain range packed into every mile of its length. A network of these strings, if it exists, would have been weaving through the cosmos since its infancy, and its influence would be colossal. Their immense mass warps spacetime so severely that they act like gravitational lenses, but with a unique property. They can create double images of distant galaxies, not as curved arcs but as perfect mirror images split along a sharp line. But their true potential for shaping the universe's fate lies in their dynamics. These strings are not static, they vibrate at nearly the speed of light, and when two strings cross, they can reconnect, sometimes snapping off closed loops. These loops are the key. According to theory, they don't just sit there, they oscillate furiously, radiating away their tremendous energy in the form of gravitational waves, ripples in the fabric of spacetime itself. Over the eons, this slow and steady energy loss from a network of cosmic strings could have a dramatic effect on the universe's energy budget and its ultimate expansion. But a more direct and violent ending could occur if two strings, or segments of a string, were to collide in just the right way. Certain types of cosmic strings are theorized to have junctions or points where multiple strings meet. A collision at such a point could trigger a catastrophic event known as a zipper instability. This isn't a simple break. It's a runaway process where the collision point itself begins to move along the strings at the speed of light, effectively unzipping them and converting their entire immense mass energy directly into gravitational radiation in a single, devastating burst. The energy released in such an event would be astronomical, potentially capable of tearing apart the fabric of spacetime on a colossal scale, creating a void of true nothingness or triggering a new phase transition in the universe's fundamental fields. This introduces the possibility of an asymmetrical end to time. A cosmic string network wouldn't be uniformly distributed. It would form a complex web across the cosmos. The end wouldn't come for everyone everywhere at once. One region of the universe might be utterly annihilated by a zipper event, while another region, far from the network, continues on toward a cold heat death for eons longer. Time wouldn't end with a single, universal clock striking midnight. It would be more like lights going out neighborhood by neighborhood in a vast, darkening city. In this scenario, the universe's finale is not a foregone conclusion written solely by dark energy, but a chaotic and unpredictable drama whose final act could be directed by these ancient, primordial scars stretching across the sky. This brings us to a theory that is perhaps the most personally unsettling thought experiment on our list, one that twists the knife of quantum mechanics to propose a form of forced, subjective immortality. It's called quantum suicide, and it extends the many worlds interpretation of quantum mechanics into a deeply disturbing and seemingly inescapable logical conclusion about your own conscious experience. The core question it raises is simple yet terrifying. Could you, from your own first-person perspective, ever actually witness the end of time? To set the stage, we need to revisit the many worlds interpretation. As we discussed earlier, this view suggests that every time a quantum event has multiple possible outcomes, the universe doesn't choose one. Instead, it splits, branching off into a new, parallel reality for every single possibility. When you flip a coin, the universe divides. In one branch, it lands heads, in another, tails. Both outcomes are equally real, and both versions of you continue their lives unaware of the other. Now, imagine a grim machine is built. It's called a quantum suicide device. In each second, it triggers a radioactive atom to decay or not decay, a perfect 50-50 quantum event. If the atom decays, the machine fires a lethal bullet. If it does not decay, the machine does nothing, and a counter clicks over to mark one more second of survival. You place your head in the device and activate it. From a third-person, objective perspective, the outcome is obvious and brutal. After just a few seconds, in the overwhelming majority of newly created branches, you are dead. Your body is there for others to find. But the theory of quantum suicide asks a haunting question about the first-person, subjective perspective of the person in the machine. What does you experience? Your conscious awareness can only follow a path where you continue to exist. You cannot experience a universe in which you are dead. Therefore, with each tick of the machine, your consciousness is forced into the branch where the atom did not decay. You would hear the counter click again and again forever. From your point of view, you would seem to be impossibly, miraculously lucky. The machine would appear to fail to fire second after second for years, then centuries, then millennia. You would become a prisoner of your own consciousness, forever locked onto the increasingly improbable timeline where you continue to survive. Now, scale this chilling idea up from a laboratory device to the entire cosmos. The universe is full of potential lethal events, from asteroid impacts to supernova explosions. On a long enough timeline, the survival of any individual conscious being relies on a continuous chain of incredibly unlikely quantum events going their way. The many worlds interpretation suggests that for every such event, there is always a branch where you survive, no matter how astronomically small the odds. Your conscious experience, therefore, is perpetually hijacked, always following the path of continued existence. You could not die in a car crash because your awareness would jump to the branch where a quantum fluctuation caused you to break a millisecond earlier. You could not be killed in a natural disaster because your consciousness would find itself in the reality where you were miraculously elsewhere when it struck. Apply this to the ultimate cosmic endings we've explored. As the universe approaches heat death, conditions become utterly hostile to life. But could your conscious experience persist? The theory suggests it might. You would find yourself on the one in a Googleplex timeline where a random quantum fluctuation reassembles the particles of your brain and a suitable environment around you over and over again. You would witness the last stars fading, not as a distant observer, but as a lone consciousness sustained by perpetual statistical miracles. You would experience the evaporation of the last black holes from a pocket of reality that should not exist, your mind preserved in a cosmic state that is, for all intents and purposes, already dead. Your personal timeline would extend into the eternal darkness, a single, unbroken thread of awareness forced to witness the final, silent act of everything, forever alone in the void. This isn't a theory of salvation. It's a theory of the ultimate existential trap, where the very laws of physics conspire to make you the universe's final and only witness, unable to ever close your eyes. But what if the universe we inhabit is not just a simulation, but one that is periodically maintained? This possibility leads us to Theory 28, simulation reset theories, which reframe the end of time not as a final deletion, but as a routine reboot. Instead of a permanent shutdown, our reality might be subject to periodic resets or upgrades, where time itself reaches a cyclical endpoint, only to begin again with its fundamental information, or even the consciousness within it preserved across iterations. Imagine the universe not as a one-time project, but as a continuous experiment or an ongoing piece of software. The operators or programmers of this simulation would have compelling reasons to reset it. Perhaps the simulation has a specific purpose, like running a complex calculation to its conclusion or observing the evolution of intelligence. Once that objective is met, the most efficient course of action isn't to shut down the entire system, but to wipe the slate clean and start over with slightly adjusted parameters to see how the story unfolds differently next time. Another reason could be routine maintenance. Even the most advanced simulation might accumulate errors or entropy over vast stretches of runtime, requiring a periodic refresh to ensure its stability and fidelity. A reset purges corrupted data, resets accumulated errors, and restores the system to its optimal initial conditions. This concept transforms the nature of a cosmic ending from something absolute into something procedural. The end of time would be a scheduled event, a pre-programmed milestone in the simulation's code. For us within the simulation, it might appear as any other cataclysm, a big crunch, a big rip, or a vacuum decay, but these would merely be the visual and physical effects of the shutdown sequence. The universe wouldn't be being destroyed, it would be closing down for a restart. All the data, the positions of every particle, the state of every field, could be saved to a cosmic hard drive before the power is cut. Then, with a new set of initial conditions, the simulation boots up again. The Big Bang is not the beginning of everything, but the beginning of the current run. The most profound implication of this theory involves the nature of consciousness and identity across these resets. If the simulation's data is preserved, then in a sense, so are we. Every thought, every memory, every person that ever lived could be saved as information. In the next cycle, that information could be reloaded. This opens the door to a form of digital reincarnation, where your consciousness is not annihilated but is instead reinstantiated in a new version of reality. You might wake up in a universe with different physical constants, a different history, or even a different body, yet still retain the core essence of who you are. The end of time becomes merely a transition, a doorway between one existence and the next, all within the grand architecture of the simulation. This idea also offers a potential solution to one of the great mysteries of our cosmos, the fine-tuning of the universe for life. The physical constants seem perfectly calibrated to allow for stars, planets, and conscious beings to exist. From a reset theory perspective, this isn't a miraculous coincidence. It's the result of trial and error. The simulation may have been run countless times before with different settings. Most of those runs likely produced barren, stillborn universes where life never had a chance. The programmers simply kept adjusting the parameters and resetting the simulation until they finally achieved a universe complex and interesting enough to observe ours. We exist in a universe that has passed the test, a successful iteration in a long line of failed attempts. The end of our time may simply mean we have served our purpose and the programmers are ready to initialize the next experiment. But for all the cosmic violence of a big rip or the silent stillness of heat death, these theories still operate within a framework where time itself, as a dimension, remains coherent. What if, under the most extreme conditions imaginable, the very fabric of time could develop flaws, kinks, tears, or points of infinite curvature that render its flow completely meaningless? This brings us to the deeply theoretical and mind-warping concept of temporal singularities, a possibility where time doesn't just end, but where its very definition breaks down. We're familiar with singularities in space. At the heart of a black hole, according to general relativity, matter is crushed to a point of infinite density where the laws of physics as we know them cease to function. A temporal singularity is a similar cataclysm but for time itself. Instead of a point where space is infinitely curved, it's a moment where time becomes infinitely curved or undefined. Imagine time not as a smooth, flowing river but as a map. A spatial singularity is like an infinitely deep pit on that map. A temporal singularity would be like the edge of the map, a point beyond which the very concept of further has no meaning. It's not a location in time, it's a boundary beyond which time cannot be extended. How could such a thing occur? One potential pathway lies in the behavior of certain exotic materials in the universe. We've already discussed phantom energy, the substance that could drive the Big Rip. The mathematics of a phantom energy-dominated universe don't just predict that galaxies will be torn apart. They predict that as the Big Rip singularity is approached, the expansion rate of the universe will actually become infinite. This isn't just a very fast expansion, it's a point where the equations of general relativity blow up. At this moment, the Hubble parameter, which measures the expansion rate, diverges to infinity. This creates a singularity not just in the density of the universe, but in the very evolution of time. The progression of time, as measured by the cosmic clock, would hit a point where a finite amount of proper time for the universe corresponds to an infinite amount of what we would call cosmic time. It's a moment where the clock stops ticking not because it runs down, but because the mechanism of the clock itself shatters. Another, even more exotic possibility involves the collision of cosmic strings or the formation of other topological defects in spacetime. These incredibly dense, one-dimensional remnants from the early universe could theoretically warp spacetime so severely that they create closed time-like curves paths through spacetime that loop back on themselves. Under the right conditions, a network of these could become so complex and dense that the light cones of individual points in spacetime, which define the future and past, tip over until they overlap completely. At this critical point, the distinction between cause and effect would vanish, and the forward march of time would be replaced by a chaotic jumble where future events could influence the past. This wouldn't just be time travel, it would be the complete breakdown of chronological order, a state of pure causal paradox. Time as a linear sequence would effectively end, replaced by a self-contradictory and inconsistent knot that no physics could unravel. The most profound implication of a temporal singularity is that it represents a true, hard boundary for physics. At a spatial singularity inside a black hole, we hope a theory of quantum gravity will eventually explain what happens. But a singularity in time is different. It's not a place where things happen, it's a place where happening itself stops. There is no after a temporal singularity, just as there is no north of the North Pole. It is the ultimate finale, not just for the contents of the universe, but for the stage upon which the cosmic drama is set. In this view, the universe doesn't fade away or cycle back. It simply reaches a point where the story can no longer be continued, because the very dimension that allows for a narrative time has met its own irreversible and absolute end. But for all the grand and terrifying finales we've just explored, from the silent stillness of heat death to the violent unraveling of a big rip, every single one of them shares a critical, humbling assumption that our current understanding of physics is essentially correct. Our 30th and final theory is perhaps the most important of all, because it is the one that acknowledges the vastness of our own ignorance. We must confront the very real possibility that we are like ancient mapmakers, drawing dragons at the edge of a world whose true shape and size we cannot possibly comprehend. The true end of time might be something so far beyond our current scientific speculation that we lack even the language to describe it, hidden within the realm of the unknown unknowns. Our entire journey through these theories is built upon the twin pillars of 20th century physics: Einstein's general relativity, which explains the cosmos on the largest scales, and quantum mechanics, which governs the smallest. These frameworks are incredibly powerful, but they are also known to be incomplete. They contradict each other at the extremes, like at the center of a black hole or the moment of the Big Bang. This tells us that a deeper theory, a theory of quantum gravity, must exist. But what if that deeper theory doesn't just tweak our equations, but completely revolutionizes our understanding of a fundamental concept like time itself? We assume time is a continuous, flowing dimension, but a complete theory might reveal it to be something else entirely, an emergent property, a quantum illusion, or even a side effect of something more profound. This opens the door to endings we cannot yet imagine. Perhaps our 3 dimensions of space and 1 of time are just a minuscule slice of a higher dimensional reality. In such a cosmos, the end of our time might not be an end at all, but a transition, a folding of our local space-time membrane back into a larger bulk dimension, an event that would be as incomprehensible to us as a symphony is to a single musical note. Or consider the persistent mystery of consciousness. We have no scientific consensus on how subjective experience arises from the objective firing of neurons. What if consciousness is not a product of the brain, but a fundamental feature of the universe like space and time? The end of time could then be a collective transition of consciousness into a different state of being, a reality not based on physical laws but on thought itself, where the concepts of beginning and end are rendered obsolete. The most exciting and daunting prospect is that the true answer might lie in a discovery that has no precedent in our current science. Every major revolution in physics, from Newtonian mechanics to relativity to quantum theory, came with mind-bending concepts that were utterly unimaginable to the generations before. There is no reason to believe our journey of discovery is over. The ultimate fate of the cosmos could hinge on a principle we haven't yet dreamed of, a force or field we haven't detected, or a completely new way of relating energy, matter, and information. The universe's final secret might be guarded not by complexity, but by the sheer limitations of our own current paradigm, waiting for a future genius to have the insight that unlocks a reality far stranger and more magnificent than any ending we have dared to propose. From the silent, cold solitude of heat death to the cataclysmic violence of the Big Rip, from the cyclical rebirth of the Big Bounce to the digital ephemeralness of a simulation shutdown, we have journeyed through 30 breathtaking visions of how it all might conclude. We've grappled with timelines stretching over trillions of years, where black holes evaporate and protons decay, and we've wrestled with the bizarre quantum possibilities that suggest our own consciousness might be the universe's final, lonely witness. We've seen how ancient faiths envision a finale rich with moral purpose and divine judgment, and we've considered the modern hope that a future superintelligence might engineer an escape from cosmic oblivion. This incredible diversity of thought, spanning rigorous science, profound philosophy, and timeless theology, reveals one universal truth. Humanity's attempt to find meaning in the face of infinity is one of our most defining and noble endeavors. Contemplating the ultimate end is not an exercise in nihilism or despair. Rather, it is the very thing that frames the breathtaking value of our present moment. Knowing that every star will one day fade, that every structure will one day dissolve, casts the here and now into a brilliant, precious relief. The fact that we are here at all, a flicker of conscious awareness in the vast dark, granted a sliver of cosmic time to think, to feel, to love, and to wonder, is nothing short of a miracle. These theories of ending, for all their variety, are not really about death. They are a mirror we hold up to the universe, and in it, we see our own deep-seated need to understand our place within the grand, unfolding story of existence. They are a testament to our unquenchable curiosity. The search for answers is far from over. Each theory is a signpost pointing toward the limits of our current knowledge, inviting us to push further. Perhaps the true nature of dark energy will be revealed, or the secrets of quantum gravity will be unlocked, offering a new, even more incredible vision of our cosmic destiny. The conversation itself is what matters most, the shared wonder at the scale of it all. So we want to hear from you. Which of these 30 theories resonates most deeply with you? Does the heat death's eternal stillness feel the most inevitable, or are you captivated by the cyclical promise of a big bounce? Perhaps the simulation hypothesis or the idea of a cosmic consciousness speaks to your view of reality. Share your thoughts and your own favorite theories in the comments below. Let's continue to explore the furthest reaches of possibility together. If your mind has been expanded by this journey to the edge of time, then you are exactly where you belong. This channel is dedicated to exploring the universe's deepest mysteries, from the nature of black holes to the origins of consciousness. We have so many more incredible adventures ahead, and we don't want you to miss a single one. Make sure to subscribe and hit the notification bell so you can join us for our next investigation into the unknown. Thank you for watching, and remember, no matter how the story ends, the fact that we get to be a part of it right here and right now is the greatest wonder of all.